Okay, welcome to another module of Pic16F877. This is analog to digital, and first we will have a look at what is analog to digital, or we can call AD. Example, in this picture we have the a sensor. We call it the photoresistor. Okay, depend on the strength of the light of the pin. This will produce the analog voltage here, and from the analog voltage we will input into our chip, and it will change to the digital signal here. And the analog signal, there are a lot of components that can produce the analog signal. This is position of needle, rotation angle of the gear, amount of water in the vessel, or electric charge. And to use the AD module in our chip, here we can see that in our PIC, the AD module is represented as the AN and X is the number of channel. Example, here we have in our PIC we have A channel. Okay, we have A channel. This is here, right? We have A channel, so that means we can read a analog signal or a analog sensors. And first of all, we will have a brief review about how to convert from analog to digital signal. Example, here we have the signal, the analog signal. The analog signal can produce the voltage from 0 to 7.5 voltage. And example, we can digitalize this analog by 4 bit here, and with 4 bit we can read the voltage like this. Okay, and example here, if the voltage drop inside example 0.4 voltage, the analog signal, the digital signal will be also 000. So the number of bits here is very important. It's called the resolution of the converter. The resolution is higher. Example 10 bit or 8 bit. The number of the reading here will be smoother. Example, if we have the 10 bit here, then we can read a smaller signal, smaller voltage. And the equation for the analog to digital signal is this one. Here is A divided V max equal to D divided M. This is the analog value. V max is the maximum value that the component can produce. D is the bit, the number of bit here. Okay, digital encoding. And M is example, we have the N is the number of bit. So we have M equal to 2n minus 1. Example, we have the analog signal that can produce from 0 to 15 voltage, and we use a bit digital signal. So we calculate the correct encoding for 5 voltage. So that means when 5 voltage, what is the digital signal here? Okay, so we will apply the equation here. Because we use a bit data, so M equal to 2 power a minus 1. Okay, so that means A is 5 voltage. We want to find V max is the maximum voltage that the component can produce. D is the number equal to A here, and M is 2 power n minus 1, and we will find d equal to 85, or the binary will be this one. So the chip, our PIC will digitalize this number into this one, and when we read this number, this digital number, we will know that okay, this one is 5 voltage. So our PIC have a 10-bit mode and 8-bit mode. So normally we will use 10-bit mode because they have more resolution. Okay, so when we use 10-bit mode, and the maximum voltage of our PIC is 5 voltage. This is 3 there, right? And so the resolution is 0.0048 voltage. Okay, so that means the voltage change just amount 4.8 millivolt. The PIC will know. The PIC will know. So the 4.8 millivolt is also a very small one, very small voltage. And this is the flow chart or the diagram of the analog to digital converter. And inside here we can see that we will have some bit related to the AD converter. This one, first one is this one, right? And the second one is this one. Okay, second one is this one. And the result, that's the result of the converter will store in two register. This here. So we will go to the the AD con 0 register first. This is the address 1F, and here we can choose the this one is the type, the conversion clock select bit. This one we will, according to our degree store, we will choose which one here. So next I will explain to you how to choose it. And the bits from CXS2 to CXS0 is to choose the channel. That means to choose the pin. We will read. And the last one is AD on. That means we enable the converter. Enable the converter. Okay. And this is the AD con 1 converter register. Okay. This one is related to select the digital or analog mode for the pin, right? If we want the pin A2 is analog, we have to choose this one. Okay, we have to choose this one, right? I think that this register is very familiar to you because you already use it in the digital input and output function. And now this is the result. And the result, because we have the 10 bit, but so we need two register to store the value. So 2 register, it is 16 bit. So we have 2 modes to store. First one is right justify, and this one is left justify. If we choose the right justify mode, the result will store in this format. And this one we choose by the ADFM bit of the AD con. Okay, and if we choose the ADFM is 0, the result will store at this format. Okay. And now how to choose this bit. Previously I already told you that is will based on which crystal you use, right? So let's see. This will related to something like TAD. This is the conversion time for 1 bit. That means when we have the 10 bit, right? It will need time to convert the analog signal to 10 bit. Each bit, this is TAD. So the total time for the conversion of 10 bit is about 12 TAD here, the 12 TAD here. Why the 12 TAD is related to this table, you can see here, right? So your task is to choose the TAD, choose the TAD that is much bigger or equal to 1.6 microsecond. That means example, if you use the big 4 megahertz, so what 4 megahertz, so the TOSC is 0.25 microsecond. So that means if you choose 0, 1, this bit 0, this bit 1, it will equal to A multiply this number, so it will equal to 2 microsecond. That means bigger than 1.6 microsecond. Okay, so that means you have to choose this one, or this one, at least bigger than 1.6 microsecond. You cannot choose this one, you cannot choose 0, 0, because when you multiply it will just equal to 0.5, it's smaller than 1.6 microsecond. So the AD conversion time will equal to about 11.5 or 12 multiply 2 microsecond equal to 23 to 24 microsecond. Okay, total 4. And this is the conversion time. We need the time for acquisition. That means the time to read this, the analog value. The time to read is equal to this equation, and this will equal to 19.75 microsecond. So the total time for one conversion, that means acquisition time and conversion time, will be plus this number, and then you have to wait at least 2 TAD to have another acquisition and another conversion time. Okay, and you see the the procedure to use the AD module. First, config this one, choose the analog module, choose analog mode, right? And then we choose the conversion clock, right? And then we turn on the AD converter. And then if we use the interrupt, we will have to clear this bit, set this bit, and set this bit, right? And then to receive the signal, we select the AD input channel by using this register. Okay. For the acquisition time, we have to wait for the AD conversion to complete by check this bit, okay. And then if this bit go down, we will read this register, read the register to know the value, and then we will go back to wait another. Okay, and this is the example code for the AD converter. First, we define the address, right? And this one is the address of the bit, right? And then this is the address of the result, right? This is the address of the result. And this one is the go down bit. Okay, go down bit. And this is the option register and inner register. This is for interrupt. So in here we don't have interrupt, so we can delete it. Okay, so the first one is to choose right here, right? Here which one? Here is I choose the the pin 0 A0 is the analog here, analog mode, right? And I choose the channel 0, this is A0 here, and this is the result, right? And if it's finished, that means this bit equal to 0, this bit equal to 0. I will read the result here, right? Because as here is I use the ADFME1, this is the right justified. Okay, this is more complicated. Okay, this is left justified, sorry, this is left justified. So the result will be, this is the ADS low bit, right? Low A bit, right? And this one is multiply, right? Okay, and then I print the result here. Okay, this is very easy. Okay. And in the CCS compiler, we just need to concentrate on for function. First is set up ADC channel. This is ADC port. This one is here, right? So here this is, here we choose the AN0 port, right? AN0 port. That means this one we choose the digital, the analog mode for the pin AN0, right? And then we set the speed, the conversion clock, and then we choose the channel 0 to read the value. And here we just read the value here. Okay. And we can see the demonstration. Okay. Here, right? Here I change the value of the resistor. You can see, right? Because this is 10 bit, right? 10 bit. In AD converter, we have another case very popular. That means because the voltage here we use these 5 volt, but some sensor they just use 3 volt as the maximum voltage. So we have to connect it at the reference power for read AD. So if we have the 3 voltage, the sensor 3 voltage, so we have to connect to this pin minus and this pin, the power source of the sensor have to connect to this pin. So we choose the reference mode. We choose the reference, and to choose the reference power mode, we have to use the Pic16F877 to Pic16F877. We have this one in the table. We must have this one. Okay, let's have this one. So example, we use the A0 as the analog input, and we use this one as the reference power. So okay, we have to choose this one. Yeah. And in the CCS compiler, for the setup ADC port, they already define for you the name here. You just pick up and use it. Example here. This is just the example. This is the power of the microchip, right? This is 5 volt, and I use 12 volt as the reference voltage. So pay attention that this is just the simulation, so we can use 12 volt. In the reality, we must use the power source smaller than 5 volt, right? This will work. Here it's just 12 volt for the simulation. Okay. Here the power, I connect the plus into pin 3, right, and the minus to the ground, right? And I have to connect the ground of the 12 volt and the ground of the 5 volt together. Okay. And let's see the demonstration simulation. Yeah, this is 12 volt, this is the reference, right? In the middle, 6.6 is equal to 563, okay?